Oh, do you know that one?
No, I got it wrong one time you asked us.
Electric blue.
Electric blue. That was my next guess.
Kind of like when you get the sun just sets and you get the blue colored sky that she really likes that. But she generally likes any color blue. But anyway, the first things first, what I'd like to do today here, yes, we don't have an exam till next week. We're ahead of the schedule. So I'd like to introduce you to something to continue on with our orbital pi orbital diagrams, but introduce to you to why the allylic cation is so stable. Then I'd like to complete the lecture for IR yesterday so we can come in tomorrow and just do problems. So now, let me show you something here. All right, the allylic cation. Let's do the line angle for me here. Or if you're to draw it out. Okay, something like this. This is capable of resonance, right? We could put this electron pair over here and bring the positive charge over on this side if we wanted to. But here's the question. How do you construct the pi orbitals here? First of all, how many p orbitals do we have in the pi system for the allylic cation? Given this, any charge or any radical is in a p orbital, not a hybridized orbital. So how many p orbitals do we have in this system?
1, 2.
How many p orbitals do we have? 3. Remember, this is contributing a p orbital at this atom. However, because it's a positive charge, it's not contributing an electron. So the orbitals we're starting with, we have these here. So first of all, so the bonding orbital for the first one, how many nodes should we have in the pi system? How many nodes? How many nodes should we have?
2, 3, 4.
I'm trying not to make a dirty symbol here by doing this, because I know that some about this is dirty, but I don't know what it means. I've heard about being, never mind, I've heard about being dirty before, but I just don't know why it's dirty. 0. Okay? This is psi 1. Okay? Now here's the problem with the second one. How many nodes should we have? As they go up in energy, they increase by how many nodes at a time? 1. So you should have 1 node and then 2 nodes. Now here's the problem. With the allylic system, this should have 1 node. The node is right at that carbon atom for this one. So the bonding orbital, the fully bonding is this one. Your node is here, so you have a shaded here, shaded down here to get your node. But the node is at a carbon atom. That is very much possible, especially when you have an odd number of p orbitals in the system. And then for this one, you should have 2 nodes, right here, right here. What do we got? This, and then this. So, psi 2, psi 3, this is the designation. In this pi system, how many electrons do we have? How many electrons in a pi bond? 2. This has none. It's positive charge, so it's contributing none to it. So we have 2 electrons. They're down here. Now remember, in these diagrams, assuming you're in the middle of the diagrams, you're at the non-bonding level. So psi 2 here, or this molecular orbital, is actually at the non-bonding level. In other words, it is an MO, it is a molecular orbital, but it's at the same energy as an isolated carbon atom. So it contributes nothing to the stability of the molecule, but it doesn't destabilize it either. Okay. Now, what if we go to the allylic radical? We've already found out with our halogenation that one's more stable than a tertiary. Where would that electron go? You cancel out the positive charge and just put an electron in there. Where do you put that next electron? Right here. So it is a radical, but it's in a non-bonding orbital, right? It's not destabilizing. That's why the allylic radical is stable. What if that's where the allylic anion, put a lone pair here, negative charge. Where did the extra electron go? The extra electron here, where would it go? Here or here? Here or here?
Second.
Second. So the allylic anion is still putting an electron in a non-bonding orbital, nothing in the antibonding orbitals yet. So that's why all three of these, this one, and this one, are stable. Putting electrons in the non-bonding orbital, they have a place there, but they don't destabilize, but they don't give extra stability. So these really have, non-bonding orbitals really have no effect, but the main electrons are in the bonding orbital, so that's what's dominating the whole thing, making all these relatively stable. But this is how I wanted to show you how you can get a non-bonding orbital. So I hadn't shown you that, not even freshman chemistry. We just assume it's non-bonding, but I didn't show you how you get it. But the only way to get one node in this is if the node is at one carbon atom here. In other words, no p orbital contributing here. But that only happens when you have an odd number of atoms. If you have an even number of atoms, there's going to be no MOs at the MO. Or no, right here. So the non-bonding level, no molecular orbitals there. So only with odd number of carbons do you get that. That's one thing I wanted to show you, given what we had done the other day. Now, for fun, I know I must be insane to think this is fun, but I don't know. But if we go any further in the lecture, we'll be 2 days ahead. I don't want to get that far ahead. 2 days ahead in here, but we're a little bit behind in the lab. So let's finish up the lab lecture. Okay, everybody get this here so far. Need more practice, I understand that. You're going to get plenty of practice, don't worry about it. Now, where we left off, in calculating degrees of unsaturation. Remember, the one thing I was thinking about yesterday, well, what do you mean by saturated and so on? Every atom has the maximum number of hydrogens they can possibly have in their compound. That's saturated. Unsaturated is when you take the hydrogens away. Now, I said where I left off was with oxygen. What do you do with halogens? Fluorine, chlorine, bromine, iodine. What do you do with them? Replace them with hydrogen and do your calculation. Remember, it's a fake formula that you're coming up with. Okay? But it makes it easier to calculate it. With oxygen, you do nothing. Why? We already established that. It really doesn't change the bonding structure of the carbon. But guess what? What do you do with sulfur? Nothing. What do you do with selenium? Nothing. Tellurium? Nothing. Whatever you do with the first element in that row, it applies to all the rest of the elements. No matter how complicated the structure is, because they can see the octet. Well, even with this, they still don't really change the R value here. Okay? Double bonds basically are on sulfur, not carbon. Degrees of unsaturation are for carbon that we're dealing with. So for oxygen, do nothing. So for example, let's do C5. Here we go again. Oh, we'll practice it in a minute. Here comes the complicated one. Always complicated. Nitrogen. But this applies to everything in that family. For nitrogen, hold on a minute. Water is H2O, right? Alcohols, CH3-OH. Right? Oxygen has no effect because it's only what we call divalent. In other words, only two shared pairs in a neutral compound. What's the equivalent nitrogen structure to this? If we take this oxygen out and put a nitrogen there, what else do we have to add? Compared to this, we had to add an extra hydrogen, right? For every nitrogen in your saturated formula, you have to add an extra hydrogen. So for this one here, C4H8, C4H9, or this one here, C4H10. Now this is 2n plus 2, so if we have 4, 2 times 4 plus 2 equals 10, right? So that's a saturated formula. But this one, 2 times 4 plus 2 plus 1 for the nitrogen. What do we get? 11. So this number comes in for every nitrogen you add an additional hydrogen. Because nitrogen is trivalent, unlike oxygen being divalent. So you put nitrogen in there, you have to add an extra hydrogen for every nitrogen. What do you do with phosphorus? Same thing. So if we look at this here, let's take a look, let's do a calculation here. With this formula, what's the saturated formula for this? It's this one up here. So how do we calculate degrees of unsaturation? This is your saturated formula. So number of hydrogens in the saturated formula is 11 minus
12. 9.
9 divided by 2. So this is 2 divided by 2 or equals 1. See, this formula won't work if you don't add that extra hydrogen for the one nitrogen there. Nitrogen always throws everything off, folks. Always does. What's wrong?
Is the answer always 1?
No. But funny you should mention that. There's certain degrees of unsaturation when you come up with it. Like if you come up with a degree of unsaturation of 4, chances are pretty good you have an aromatic ring. That would take care of all 4. 4 or higher, you may have an aromatic ring in small molecules. It's very common. Why? Take a look at benzene. How many rings? 1 ring. How many double bonds? 3. This is a degree of unsaturation of 4. So if you have a small molecule, you come up with a degree of unsaturation of 4, and you got at least C6 in there, you got a benzene ring somewhere. So no, it's not always 1, but sometimes these nice little numbers here give you a clue as to what's there before you even look at the IR. What's wrong?
Where did the 9 come from? Oh,
This 9 here? Okay.
no.
Okay. Now examples. For this one, how many degrees of unsaturation are in C9H11 I2N? What's the first thing you do? Take out the iodines, put hydrogen in there for calculation purpose. This is the actual formula. We're just doing a calculation here. There's your saturated formula, getting rid of the iodines. Now what do? What's the saturated formula for this? First of all, how many carbons do I have?
9.
9. So I have 9. But so 2 times 9 plus 2 plus what?
4.
1 for the nitrogen. So that's 18 plus 2 is 20 plus 1 is 21. That's where this goes.
So you don't have to do anything with the pregnant?
Once you replace it, you're done. Simply put, halogens act like hydrogen in the compound when they're just a simple monatomic hydrogen or halogen. Take hydrogen, put a formula in its place. Did it change the carbon structure? No. So CH4 or CH3F has the bonding to the carbon atom changed? No. All single bonds. Fluorine is just substituting for hydrogen. That's why you go back here to do the calculation. I used to have people do it, need a halogen there, but it always confused the heck out of people. It's easy to just get rid of it. So, 2 iodines, 2 hydrogens, 13. Done. Now, so we have 21. So how do you calculate degrees of unsaturation before I do it in the slide?
So then take 21 minus 13. Or is it 11?
21 minus 13, divided by 2. Yeah, once you've done this, this is what you use in the calculations. So U is equal to that. What do we get? 21 minus 13 is what?
8.
8 divided by 2?
4.
Whoops. What did I just say a minute ago? What's likely there?
Ring.
A benzene ring. So I've done that, and there it is. But the thing is, what the degree of unsaturation formally means, 4 rings, 4 multiple bonds, or any combination thereof. By the way, a degree of unsaturation of 2. What does that mean? This doesn't have it, but if you come up with a degree of unsaturation of 2, what does it mean? Possibly 2 rings, right? 2 double bonds, a ring and a double bond, or a triple bond. And this keeps doing this to me. I'm starting to get annoyed. How many degrees of unsaturation does a triple bond have? 2. The first one's sigma, so that doesn't count. Only the pi bonds count for unsaturated. So if you have a degree of unsaturation of 2, you see that number, now you can say, wait a minute, is there possibly a triple bond here? It may not be, but you start thinking that way. And there's the actual structure. One of the examples I had done previously. Here's your benzene ring. And it kind of makes sense. A degree of unsaturation of 4 with only 9 carbons, it takes 6 to make a ring. This small molecule, that 4 is almost pointing right to the benzene ring. Now, where these things are on the ring, that you can't tell from this. Okay. All right. What's wrong?
You're good.
I missed the joke.
That's okay.
Okay.
That's a really joke.
All right. So with IR in the molecular formula, you can tell a lot about the compound. I'm just going to skip through this here. Skip through these because I've already given these. You can look them up where everything occurs. Remember their approximation. So let's do an example here. First of all, what's the degree of unsaturation with this? So N is what? 6. So 2 times 6 plus 2 equals 14. 14 minus 12, because we don't have to do anything with oxygen. Divide by 2, what do we have?
1.
1. 1 degree of unsaturation. What could it be? What are the possibilities? Could be a double bond. Do we see evidence of double bond here right around 1660? No. That's kind of noise. A ring. Okay. I can say it's a ring. What else is there from the IR? Take your time.
What's the thing about when the peaks are like almost equal?
Oh, with the aromatic ring, when you have a 1500 and 1600, we don't have that. With a cyclohexane ring, you're not going to see that 1600 and 1500.
Something on the left and the right of 2000.
Well, if we do this right here, this is talking about alkyl groups. Of the CH stretch, that's the ring. No, you gotta play that out. Got it?
Is there an OH stretch?
Thank you. Right there. So the structure is this structure consistent with the molecular formula and the OH group of an alcohol showing up in this region here. If you look previously what alcohols look like, that looks very much like an alcohol, an OH peak. Also notice OH peaks tend to be more rounded down here, where an NH peak sometimes goes a little bit more sharp. Or a little bit more triangular and a little bit more sharp at times. But from now on, when you see this peak right here, think OH. If this were an acid, it would be broaden out a little bit more like that. If it's just broadened only up to like 3,000, it's not an acid. What's this peak here and these peaks here? Junk. I have no idea what they are. That goes a little beyond me. And now, don't confuse this as actually being an aldehyde. This thing is actually a little too low. I can see that happening with this group here. Not very distinctive. Ready for another one?
Yes.
Here we go. Calculate degrees of unsaturation. What do we got?
2 times 14.
Two times, whoops. 2 times 6 plus 2 equals 14. We have 14 minus 10 divided by 2 equals what?
2.
2. So what do we have? What's that? What's that? Possibly a triple bond? Let's check the possibility. Right around 2,500. Do I see a big peak here? Do I see a peak like this? No triple bond. Or it's symmetrically arranged that you can't see it in IR. You'd only have to have NMR to see it. Good guess though. Triple bond. Or, now it can't be this, right? Because we don't have nitrogen in the formula. This one, unless it's symmetrically arranged so we can't see it, I'm saying this is unlikely. And the reason for it, because there's a peak here that's showing you what one of the degrees of unsaturation is. In IR, the first thing to look for is not necessarily the alcohol peak. By the way, this is junk. Don't worry about it. I have to tell you that because the compound wasn't pure. What's in the middle, in this structure here is right smack dab in the middle of the spectrum. C double bond O, right here. Carbonyl group. What's this number here? 1,500, 1,600, 1,700? Now, since you can't read the number very well, it looks like it's not 1,700. It looks more like 1,710, but just to the left of 1,700. If it were here, that'd be an ester. If the bottom of the peak were over here. So this could be a ketone, aldehyde, or acid. Any acid OH groups over here? No. So it's not an acid. And aldehydes would have some definitive peaks right around here that they're missing. No aldehyde peaks here. No, like that. So I have a C double bond O. We have one more degree of unsaturation, right? What are these? Just to the right of 3,000. CH. Alkyl group. A lot of them. Any CHs of an alkene? Or an aromatic? So we have double bond C double bond O, but no evidence at all of a carbon-carbon double bond. So what else could we have? No evidence of carbon double bond because there's nothing right here. This right here is more of a resonance of the CO. Don't worry about it. This peak here. Don't worry about those. What else could we have? 1 degree of unsaturation C double bond O. 1, so we got this. We have 1 left. No evidence of a carbon-carbon double bond. What could it be? Not a benzene ring. Not an aromatic ring. Cyclohexane ring. And where would you put this double bond O? So I've used all 6 carbons, right?
How do you know that?
What's that?
How did you figure that out?
I made it up. I made it up. No, but how do you figure it out? See, we have a C double bond O in here. That takes care of one of the degrees of unsaturation. The other degree of unsaturation, well, you can have a carbon-carbon double bond, but there's no evidence of carbon and hydrogen stretch of a double bond here. No carbon-carbon double bond actually showing up right around here, where it's supposed to. Only one other possibility. And then we can do this. So we don't add any extra carbons. Cyclohexanone is the name of this compound. Cyclohexanone. But now you got the intro to the IR. Let's do another one. These are pretty hard. In fact, the simpler the structure, the harder they are. Really. So what's the first thing you do to this?
What do you do with you?
Halogen. Get rid of it, replace it with hydrogen. So this is C6H14, but isn't that the saturated formula?
Yep.
Degrees of unsaturation, 0. No double bonds, no rings. And we have bromine there. So what? These would be indicating where the bromine is if we had more experience. I just know that they are, but I don't know what it really means. So where would you put the bromine? Lashana, where do you want to put the bromine? You have a 6-carbon chain, no rings. Where do you want to put the bromine? Make a guess. Got 6 carbons here. Where do you want to put the bromine? On the right? Right there? The rest being hydrogen? Sometimes in spectroscopy, what I do is I draw out the full Lewis structure, put the function groups in, and then fill in the hydrogens later. Could you put it there? Is that a consistent formula? Okay. What if I put it at position 2? Will it still be consistent? How about position 3? If you go over here, you start repeating. So is it 1 bromo, 2 bromo, 3 bromo? Don't know. IR doesn't tell you. NMR will. So here, if one of you says, well, I'm going to make it for carbon 1, well, I'm going to make it carbon 2, I'm going to make it carbon 3, I give you all full credit. Because you don't have enough information to decide. Once we have NMR, you will have enough information. Oh, first of all, ready for another one?
Yeah.
And this has to give you a point. Whenever you see in a formula in NO2 like this, you have the possibility of an and I'm going to do formal charges here just simply because you have a positive on nitrogen, negative on oxygen. Formal charge. Abbreviated as NO2 or a nitro group. New function group memorized. We haven't done it before. How many degrees of unsaturation does this have? Or would this contribute? It's doubly bonded here in Lewis structure, just the one. Now it's in resonance with this, but you still only have one double bond. Okay? So I have to get that there because we haven't discussed it before. So now, let's calculate. 2 times 6 plus 2. What do we do for that nitrogen? Plus 1 more. Only do that with the nitrogen. Otherwise, it's 2n plus 2, and you're done. You put nitrogen, add 1 for each nitrogen. That's the only. But phosphorus, arsenic, some of those do the same thing. So what do we have here? 15 for the saturated. Notice we have an odd number of hydrogens. We won't have 0.5 degrees of unsaturation here. That's why you have one of the nitrogen, so you actually get a whole number. So now we got 15 minus 5 divided by 2. What is that? 5. Whoops. big number, but you have a small compound here. What does that signify? I already said this accounts for 1 degree of unsaturation. 5 minus 1 is 4.
Nice one.
What does a degree of unsaturation of 4 mean, generally?
Ring. Benzene.
Benzene ring.
That's what it is.
That's what it is.
That's it?
Nitrobenzene. Well, the formula that small and a high degree of unsaturation like this, 4 or greater, you got to start assuming you may have a benzene ring there. Now, does the IR prove that? Pretty much. This is pretty close to 1500, and this is pretty close to 1600, but this peak here is your NO stretch. And so is this one. And I say N-O because remember, this is in resonance, so it's not a full double bond. So you have 2 of them here. Why 2? Let's draw it like this. What type of stretches do we have? Symmetric or asymmetric? I apologize, my arm cracking there. It's still healing. Starting to sink in? Okay. You have several unknowns that you have to do, but okay, summary of IR. OH peak, where would that occur? Go back to your notes, say about where it is.
Oh, to the left.
Yeah, that's about 3200 to 3600. Broad. In other words, peak like that. Right around, centered maybe around 3200 or so. Or not, 3400. Would be the center. 3200, 3600. Where would you find those?
To the right.
To the right of what?
3,000.
And the number you're given in the spectrum will be 2800 to 3000. The way the spectrum is set up, this is right at 3000, big peak. And these? Same range, right? There's the alkyl groups. Oh.
3,000? Wait, what?
So this one, so 2800 to 3000. 2800 to 3000. Those are both alkyl groups. Now what about these? 2 frequencies we're looking for. One being the carbon-hydrogen stretch. Where would the carbon-hydrogen of this be?
To the right of you.
Not to the right, but
To the left.
to the left. Of 3000. Oops. We have 3000 here. This way, it's to the right. CH alkyl group.
Yeah.
Just to the left. CH
Close with both.
alkene or aromatic. What other peak would you be looking for this? What's that? Don't know? Let's get you confused. What's another definitive peak here? So we never talked about carbon-carbon single bonds because those are in the fingerprint region. Can't identify them. It's been mostly carbon-hydrogen stretches, oxygen-hydrogen, nitrogen-hydrogen, or carbon-carbon double bond. Where would the carbon-carbon double bond be? I'd go 1650.
Oh, yeah.
Why? Or maybe even 1620. Double, single, double, single, double, single, double, single, double. What are they?
What's it called?
Starts with C.
Convergent?
Not convergent.
Conjugated.
Conjugated. Means all the electrons are spread. They're not isolated double bonds. All those electrons can move anywhere within that pi system. So 1650, 1620, because an isolated bond was 1660. But these are conjugated. So it's going to be less than 1660. All right, I can stop the recording now.